Welcome back. I'm your friend Inside XO. Today we are going to learn the Chapter 11, Neural Networks that Understand the Language. In another word, it is the natural language processing. In this chapter, we will learn natural language processing, supervised NLP, capturing word correlation in input data, introduction to an embedding layer, neural architecture, comparing word embeddings, filling in the blank, meaning is derived from loss, word analogies. Man is a slow, sloppy, and brilliant thinker. Computers are fast, accurate, and stupid. But I think that situation may get changed in the future. What does it mean to understand language? What kinds of predictions do people make about language? What kinds of predictions do people make about language? Up until now, we'll be using neural networks to model image data, but the neural networks can be used to understand a much wider variety of datasets. Exploring new datasets also teaches us a lot about neural networks in general, because different datasets often justify different styles of neural network training according to the challenges hidden in the data. We will begin this chapter by exploring a much older field that overlaps deep learning, natural language processing. This field is dedicated exclusively to the automated understanding of human language, previously not using the deep learning technology. We will discuss the basics of deep learning's approach to this field. Natural language processing, NLP, is divided into a collection of tasks or challenges. Perhaps the best way to quickly get to know NLP is to consider a few of the many challenges the NLP community seeks to solve. Here are a few types of classification problems that are common in ALP. Using the characters of a document to predict where words start and end. Using the words of a document to predict where sentences start and end. Using the words in a sentence to predict the part of speech for each word. Using words in a sentence to predict where phrases start and end. Using words in a sentence to predict where named entity, person, place, scene, references start and end. Using sentences in a document to predict which pronouns refer to the same person or place or scene. Using words in a sentence to predict the sentiment of a sentence. Generally speaking, NLP tasks seek to do one of three things: label a region of text, such as part of speech tagging, sentiment classification, or named entity recognition, link two or more regions of text, such as coreference, which tries to answer whether two mentions of a real-world scene are in fact referencing the same real-world scene, where the real-world scene is generally a person, place, or some other named entity, or try to fill in missing information, missing words based on context. Perhaps it's also apparent how machine learning and NLP are deeply intertwined. Until recently, most state-of-the-art NLP algorithms were advanced, probabilistic, non-pragmatic model, not deep learning, but the recent development and popularization of the two major neural algorithms have swept the field of NLP, neural word embeddings and recurrent neural networks. In this chapter, we will build a word embedding algorithm and demonstrate why it increases the accuracy of NLP algorithms. In the next chapter, we will create a recurrent neural network and demonstrate why it's so effective at predicting across sequences. It's also worth mentioning the key role that NLP, perhaps using deep learning, plays in the advancement of artificial intelligence. AI seeks to create machines that can think and engage with the world as humans do. NLP plays a very special role in this endeavor, because language is the bedrock of conscious logic and communication in humans. As such, methods by which machines can use and understand language form the foundation of human-like logic in machines, the foundation of thought. Supervised NLP. Words go in and predictions come out. Perhaps you will remember the following figure from the chapter 2. Supervised learning is all about taking what you know and transforming it into what you want to know. Up until now, what you know has always consisted of numbers in one way or another. But NLP uses text as input. How do you process it? What do you know through the supervised learning algorithm comes to a machine predictor. Because neural networks only map input numbers to output numbers, the first step is to convert the text into numeric form. Much as we converted the straight-line dataset, we need to convert the real-world data, in this case the text, into a matrix the neural network can understand. As it turns out, how we do this is extremely important. We have to convert the raw text into matrices. First, how should we convert text to numbers? Answering that question requires some thought regarding the problem. Remember, neural networks look for correlation between their input and output layers. Thus, we want to convert text into numbers in such a way that the correlation between input and output is most obvious to the network. This will make for faster training and better generalization. In order to know what input format makes the input-output correlation the most obvious to the network, we need to know what the input-output dataset looks like. To explore this topic, let's take on the challenge of topic classification. IMDb movie reviews datasets. You can predict whether people post positive or negative reviews. The IMDb movie reviews dataset is a collection of review rating pairs that often look like the following. This is an imitation not pulled from the IMDb. This movie was terrible. The slot was dry. The acting unconvincing. And I spied popcorn on my shirt. rating 1 star. So as a human being, I would think that this review is a negative emotional one. The entire dataset consists of around 50,000 of these pairs, where the input reviews are usually a few sentences and the output ratings are between 1 and 5 stars. People consider it a sentiment dataset because the stars are indicative of the overall sentiment of the movie review, but it should be obvious that this sentiment dataset might be very different from other sentiment datasets, such as product reviews or hospital patient reviews. You want to train a neural network that can use the input text to make accurate predictions of the output score. To accomplish this, you must first decide how to turn the input and output datasets into matrices. Interestingly, the output dataset is a number, which perhaps make it an easier place to start. You will adjust the range of stars to be between 0 and 1 instead of 1 and 5, so that you can use binary softmax. That's all you need to do to the output. I'll show an example on the next page. The input data, however, is a bit tracker. To begin, let's consider the raw data. It's a list of characters. This presents a few problems. Not only is the input data text instead of numbers, but it's variable length text. So far, neural networks always take an input of fixed size. You need to overcome this problem. So the raw input won't work. The next question to ask is, what about this data will have correlation with the output? Representing that property might work well. For starters, I wouldn't expect any characters to have any correlation with the sentiment. You need to think about it differently. What about the words? Several words in this dataset would have a bit of correlation. I would bet that terrible and unconvincing have significant negative correlation with the rating. By negative, I mean that as they increase in frequency in any input data point, any review, the rating tends to decrease. Perhaps this property is more general. Perhaps words by themselves, even out of context, would have significant correlation with sentiment. Let's explore this further. Capturing word correlation in input data. Back of words, giving a review's vocabulary predict the sentiments. If you observe a correlation between the vocabulary of an IMDb review and its rating, then you can proceed to the next step, creating an input matrix that represents the vocabulary of a movie review. What's commonly done in this case is to create a matrix where each row vector corresponds to each movie review, and each column represents whether a review contains a particular word in the vocabulary. To create the vector for a review, you calculate the vocabulary of the review and then type 1 in each corresponding column for that review and zeros everywhere else. How big are these victories? Well, if there are 2,000 words and you need a place in each vector for each word, each vector will have 2,000 dimensions. This form of storage, called the one-hot encoding, is the most common format for encoding binary data. The binary presence or absence of an input data point among a vocabulary of possible input data points. If the vocabulary was only 4 words, the one-hot encoding might look like this. Here you can see a vector or a list with 4 elements in it because the whole sentence only got 4 different words. As you can see, we create a vector for each term in the vocabulary, and this allows you to use simple vector addition to create a vector representing a subset of the total vectory, such as a subset corresponding to the words in a sentence. Note that when you create an embedding for several terms, such as the cut set, you have multiple options if the words occur multiple times. If the first was cut, you could either sum the vector for cut 3 times, resulting in 3000, or just take the unique cut in a single time, resulting in 1000. The latter typically works better for language. Predicting movie reviews. With the encoding strategy and the previous network, you can predict the sentiments. Using the strategy we just identified, you can build a vector for each word in the sentiments dataset and use the previous 2-layer network to predict sentiments. I'll show you the code, but I strongly recommend attempting this from memory. Open a new chapter notebook. Note in the dataset. Build your one-hot vectors and then build a neural network to predict the rating of each movie review, positive or negative. Here's how I would do the pre-processing step. First, we import the SYS library. We say file equal to open reviews.txt. Row reviews equal to f.readlines. We close that file stream. Then we open the label dataset, and we get the row labels. The token equal to a list of different words. And for each sentence in tokens, for each word in sentence, if the length of that word greater than 0, we add that word to our vocabulary list. Word to indexed. For the indexed and word in the vocabulary list, we get the indexed for each word. Oh no, it is another way to express that. As we could know, the word to indexed is a dictionary, and for this dictionary, the K is the word, is a text, and the value is a number. The value is numbers. The input dataset equal to an empty list for each sentence in tokens. Okay, whatever you said, I think this process is all about convert the text to unique numbers. And for the labels, it only got two different values, 1 and 0. An introduction to an embedding layer. Here's one more trick to make the networks faster. At the right is the diagram from the previous neural network, which you will now use to predict sentiments. But before that, I want to describe the layer names. The first layer is the dataset, layer 1. This is followed by what's called a linear layer, weights 0, 1. This is followed by a ReLU layer, layer 1. Another linear layer, weights 1, 2. And then the output, which is a prediction layer. As it turns out, you can take a bit of a shortcut to layer 1 by replacing the first linear layer with 0, 1 with an embedding layer. Taking a vector of 1s and 0s is mathematically equivalent to summing several rows of a matrix. Thus, it's much more efficient to select the relevant rows of weights 0, 1 and sum them, as opposed to doing a big vector matrix multiplication. Because the sentiment vocabulary is on the order of 70,000 words, most of the vector matrix multiplication is spent multiplying zeros in the input vector by different rows of the matrix before summing them. Selecting the rows corresponding to each word in a matrix and summing them is much more efficient. Using this process of selecting rows and performing a sum means treating the first linear layer as an embedding layer. Structurally, they are identical. Layer 1 is exactly the same using either method for forward propagation. The only difference is that summing a small number of rows is much faster. After running the previous code, run this code. Okay, here's a training process, or how to build the neural network model. First, we import lampy as np.return.set equal to 1. The sigmoid activation function equal to this. The alpha iteration is equal to 0.01 and 2. The hidden size equal to 100 size. The weight 01 equal to that. The weights 1, 2 equal to another one. It's all numbers. It is much the same as we have seen in the previous code. Interpreting the output. What did the neural network learn along the way? Here's the output of the movie reviews neural network. From one perspective, this is the same correlation summarization we have already discussed. The neural network was looking for correlation between the input data points and the output data points, but those data points have characteristics we are familiar with. Furthermore, it's extremely beneficial to consider what patterns of language would be detected by the correlation summarization, and more importantly, which ones wouldn't. After all, just because the network is able to find correlation between the input and output datasets doesn't mean it understands every useful pattern of a language. Furthermore, understanding the difference between what the network is capable of learning relative to what it needs to know to properly understand language is an incredibly fruitful line of thinking. This is what researchers on the front lines of state-of-the-art research consider, and it's what we are going to consider here. What about the language? Did the movie reviews network learn? Let's start by considering what was presented to the network, as displayed in the diagram at the top right. Okay, here's the top right. The label, the neural network, the review vocabulary. You presented each review's vocabulary as input and asked the network to predict one of two labels, positive or negative. Given that the correlation summarization says the network will look for correlation between the input and output datasets, at a minimum, you would expect the network to identify words that have either a positive or negative correlation. This follows naturally from the correlation summarization. You present the presence or absence of a word. As such, the correlation summarization will find direct correlation between this presence or absence of each of the two labels, but this isn't the whole story. I don't know why the other would like to give you a lot of ideas behind that, but for my opinion, I would say it's just a simple process, taking the sentences and give you two labels or two possibility choices or stuff like that. Input, network, output, that's all. Neural architecture. How did the choice of architecture affect what the network learned? We just discussed the first, most trivial type of information the network learned: direct correlation between the input and target datasets. This observation is largely the clean slate of natural intelligence. If a network can discover direct correlation between the input and output dataset, something is probably broken. This development of more sophisticated architectures is based on the need to find more complex patterns than direct correlation, and this network is no exception. The minimal architecture needed to identify direct correlation is a two-layer network, where the network has a single weight matrix that connects directly from the input layer to the output layer. But we used a network that has a hidden layer. This begs for the question: what does this hidden layer do? Fundamentally, hidden layers are about grouping data points from a previous layer into n groups, where n is a number of neurons in the hidden layer. Each hidden neuron takes in a data point and answers a question: is this data point in my group? As the hidden layer learns, it searches for useful groupings of its input. What are useful groupings? An input data point grouping is useful if it does two things. First, the grouping must be useful to prediction of an output label. If it's not useful to the output prediction, the correlation summarization will never net the network to find the group. This is a huge valuable realization. Much of neural network research is about finding training data or some other manufactured signal for the network to artificially predict. So it finds groupings that are useful for a task, such as predicting movie review stars. We will discuss this more in a moment. Second, a grouping is useful if it's an actual phenomenon in the data that you care about. Bad groupings just memorize the data. Good groupings pick up on phenomena that are useful linguistically. For example, when predicting whether a movie review is positive or negative, understanding the difference between terrible and not terrible is a powerful grouping. It would be great to have a neuron that turned off when it saw awful and turned on when it saw not awful or beautiful or awesome. This would be a powerful grouping for the next layer to use to make the final prediction. But because input to the neural network is the vocabulary of a review, it was great, not terrible, creates exactly the same layer 1 value as it was terrible, not great. For this reason, the network is very unlikely to create a hidden neuron that understands negation or negative motion. Testing whether a layer is the same or different based on a certain language pattern is a great first step for knowing whether an architecture is likely to find that pattern using the correlation summarization. If you can construct two examples with an identical hidden layer, one with the pattern you found interesting, and one without, the network is unlikely to find that pattern. As you just learned, a hidden layer fundamentally groups the previous layer's data. As a granular level, each neuron classifies a data point as either subscribing or not subscribing to its group. At a higher level, two data points, movie reviews, are similar if they subscribe to many of the same groups. Finally, two inputs words are similar if the weights linking them to various hidden neurons are similar. Given this knowledge in the previous neural network, what should you observe in the weights going into the hidden neurons from the words? What should you say in the weights connecting words and hidden neurons? Here's a hint. Words that have a similar predictive power should subscribe to similar groups, hidden neurons configurations. What does this mean for the weights connecting each word to each hidden neuron? Here's the answer. Words that correlate with similar labels, positive or negative, will have similar weights connecting them to various hidden neurons. This is because the neural network learns to bucket them into similar hidden neurons so that the final layer, the weights 1, 2, can make the correct positive or negative predictions. You can see this phenomenon by taking a particularly positive or negative word and searching for the other words with the most similar weight values. In other words, you can take each word and say which other words have the most similar weight values connecting them to each hidden neuron, to each group. Words that subscribe to similar groups will have similar predictive power for positive or negative labels. As such, words that subscribe to similar groups having similar weight values will also have similar meaning. Abstractly, in terms of neural networks, a neuron has similar meaning to other neurons in the same layer, if and only if it has similar weights connecting it to the next or the previous layers. Comparing word embeddings, what can you visualize with similarity? For each input word, you can select the list of weights proceeding out of it to the various hidden neurons by selecting the corresponding row of weights 0 and 1. Each entry in the row represents each weight proceeding from that row's word to each hidden neuron. Thus, to figure out which words are most similar to a target term, you compare each word's vector row of the matrix to that of the target term. The comparison of choice is called the Euclidean distance, as shown in the following code. Okay, as we can say, he just used a method to manage two weights or two vectors or two matrices. Then it somehow finds a way to calculate the squared value of that vector. Then he used a sum function to get the sum of that vector. Then he did another square function for that, and that's the similarity. This allows you to easily query for most similar word according to the network. As you might expect, the most similar term to every word is itself, followed by words with similar usefulness as the target term. Again, as you might expect, because the network has only two labels, positive and negative, the input terms are grouped according to which label they tend to predict. This is a standard phenomenon of the correlation summarization. It seeks to create similar representations, layer 1 values with the network based on the label being predicted, so that it can predict the right label. In this case, the side effect is that the weights fitting into layer 1 get grouped according to the output label. The key takeaway is a get instant about this phenomenon of the correlation summarization. It constantly attempts to convince the hidden layers to be similar based on which label should be predicted. What is the meaning of a neuron? Meaning is entirely based on the target labels being predicted. Note that the meanings of different words didn't totally reflect how you might group them. The term most similar to beautiful is atmosphere. This is a valuable lesson for the purposes of predicting whether a movie review is positive or negative. These words have nearly identical meanings, but in the real world, their meaning is quite different. One is an adjective and another is a noun. For example, something like this. The heart is a noun. I think the possible sentence for that word is, this movie was made by heart. It was really good. Something like that. The relation is incredibly important. The meaning of a neuron in the network is defined based on the target labels. Everything in the neural network is contextualized based on the correlation summarization, trying to correctly make predictions. Thus, even though you and I know a great deal about these words, the neural network is entirely ignorant of all information outside the task at hand. So this at least give us an important lesson about the intelligence. Your intelligence depends on what kind of goal that you want to achieve, or what kind of problem you want to solve. Yeah, that's it. How can you convince the network to learn more detailed information about the neurons? Well, if you give it input and target data that requires a more lengthed or advanced understanding of a language, it will have reason to learn more complicated stuff. What should you use the network to predict so that it learns more interesting weight values for the word neurons? The text you will use to learn more interesting weight values for the word neurons is what? It's glorified fill in the blank task. Why use this? First, there's nearly infinite training data at the internet, which means nearly infinite signal for the neural network to use to learn more nuanced information about words. Furthermore, being able to accurately fill in the blank requires at least some notion of context about the real world. For instance, in the following example, is it more likely that the blank is correctly filled by the word anyway or would, or will? Let's say if the neural network can figure it out. Maria had a little lamb whose was white as snow. I would say it's a wool whose wool was white as snow. Filling in the blank. Richer meanings for words by having a richer signal to learn. This example uses almost exactly the same neural network as the previous one, with only a few modifications. First, instead of predicting a single label giving a movie review, you will take each 5-word first, remove one word, a focus turn, and attempt to train a network to figure out the identity of the word you removed using the rest of the first or rest of the words. Second, you will use a trick called negative sampling to make the network train a bit faster. Consider that in order to predict which term is missing, you need one label for each possible word. This would require several thousand labels, which would cause the network to train slowly. To overcome this, let's readily ignore most of the labels for each forward propagation step. As in, pretend they don't exist. Although this may seem like a crude approximation, it's a technique that works well in practice. Here's a pre-processing code for this example. We still do the same thing. We import the file, and we get the tokens, and we get the vocabulary, and we convert it to numbers. Predicts only a written subset because it's really expensive to predict every vocabulary. Meaning is derived from loss. With this new neural network, you can subjectively say that the word embeddings cluster in a rather different way, where before words were clustered according to their likelihood to predict a positive or negative label. Now they are clustered based on their likelihood to occur with the same first, sometimes regardless of settlements. Okay, let's have a look at this. In the prairies, if we give it a word terrible, it will reproduce you like something boring, annoying, horrible. It's all negative. But now if we give it a terrible word, it will return horrible, brilliant, phenomenal, masterful. But at least here you got a word brilliant. It's not negative. The key takeaway is that even though the network trained over the same dataset with a very similar architecture, you can influence what the network knows within its weights by changing what you tell the network to predict. Even though it's looking at the same statistical information, you can target what it knows based on what you select as the input and the target values. For the moment, let's call this process of choosing what you want the network to know. We gave it a name about this technique. Intelligence targeting. Controlling the input or target values isn't the only way to perform intelligence targeting. You can also adjust how the network measures error, the size and types of layers it has, and the types of regularization to apply. In deep learning research, all of these techniques fall under the umbrella of constructing what's called a loss function. We were almost done. You need to have patience about this. Learning is all about taking knowledge in, but it requires you to have patience, because you can't just remember everything or understand everything overnight. It can be happening. Neural networks don't really learn data. They minimize the loss function. In Chapter 4, you learn that learning is about adjusting each weight in the neural network to bring the error down to zero. In this section, I'll explain the phenomena from a different perspective, choosing the error so the neural network knows the patterns we are interested in. Remember these lessons. The golden method for learning: adjust each weight in the correct direction and by the correct amount so the error reduces to zero. The secret: for any input and goal prediction, the exact relationship is defined between error and weight. Found by combining the prediction and error formula. Perhaps you remember this formula from the one-weight neural network. In that network, you could evaluate the error by first forward propagating and then comparing to the target. I encourage you not to think about this from the perspective of two different steps: forward propagation, then error evaluation, but instead to consider the entire formula, including forward prop, to be the evaluation of an error value. This context will reveal the true cause of the different word embedding clustering. Even though the network and datasets were similar, the error function was fundamentally different, leading to different word clustering. close things within each network. All right. You know what? For me, I think those theories are just not important for a participator. I mean, for an engineer or for a small programmer like me. I just don't care about that. I'll just use it to do the real work. All I need to know is that we can use the embedding layers. It's a layer, and you can use to convert the text to convert the text to numbers. All I have to know is that, and what's left is to use it to solve real problems. The choice of loss function determines the neural network's knowledge. The more formal term for an error function is a loss function or objective function. Considering learning to be all about minimizing a loss function gives a far broader perspective on how neural networks learn. Two neural networks can have identical starting weights betrained over identical datasets and ultimately learn very different patterns because you choose a different loss function. In the case of the two movie review neural networks, the loss function was different because you choose two different target values. Positive or negative varies fill in the blank. Different kinds of architectures, layers, regularization techniques, datasets, and non-linearities aren't really that different. These are the ways you can choose to contrast a loss function. If the network isn't learning properly, the solution can often come from any of these possible categories. So that means we have to change the layers, change the regularization techniques, change the datasets, or even more change everything that was part of that training process. Anything could have big effects on the learning process. For example, if a network is overfitting, you can augment the loss function by choosing simpler non-linearities, smaller layer sizes, share owner architectures, larger datasets, or more aggressive regularization techniques. All of these choices will have a fundamentally similar effect on the loss function and similar consequences on the behavior of the network. They all interplay together, and over time you will learn how change one can affect the performance of another. But for now, the important takeaway is that learning is about constructing a loss function and then minimizing it. Whenever you want a neural network to learn a pattern, everything you need to know to do so will be contained in the loss function. When you had only a single weight, this allowed the loss function to be simple, as you will recall in here. But as you chain large numbers of complex layers together, the loss function will become more complicated. Just remember, if something is going wrong, the solution is in the loss function, which includes both the forward prediction and the row error evolution. I don't know what's that mean. What is here? It's related to the loss function. In my experience, normally I train the neural networks. I won't care a lot about the loss function. I will just use a mean squared error or or binary entropy or categorical entropy or something like that. I don't care that too much. Kin minus man plus woman almost equal to the queen. Word analogies are an interesting consequence of the previously built network. Before closing out this chapter, let's consider what is, at the time of writing, still one of the most famous properties of neural word embeddings. Word vectors like those we just created. The task of filling in the blank creates word embeddings with interesting phenomena known as word analogies, wherein you can take the vectors for different words and perform basic algebraic operations on them. For example, if you train the previous network on a large enough corpus, you will be able to take the vector for kin, subtract from it the vector for man, add in the vector for woman, and then search for the most similar vector other than those in the query. As it turns out, the most similar vector is often the word queen. It makes sense because for kin, if you king means a powerful man that controls everything, and man means a man. Yeah, it's the man. If you minus man and plus a woman, what kind of woman would have the power to control everything? That is a queen. It is equal to a queen. Word analogies, linear comparison of an existing property in the data. When this property was first discovered, it created a flurry of excitement as people extrapolated many possible applications of such a technology. It's an amazing property in its own right, and it did create a veritable cottage industry around the generating word embeddings of one variety or another. But the word analogy property in and of itself hasn't grown that much since then, and most of the current work in language focuses instead on recurrent architectures. That being said, getting a good intuition for what's going on with word embeddings as a result of a chosen loss function is extremely valuable. You have already learned that the choice of loss function can affect how words are grouped, but this word analogy phenomenon is something different. What about the new loss function causes it to happen? Have you considered a word embedding having two dimensions? It's perhaps either to envision exactly what it means for this word analogies to work. King, man, woman, queen. King minus mine, 0.1, 0.1. Queen minus woman, 0.1, 0.2. It's almost the same. The two numbers are very similar to each other. The relative usefulness to the final prediction between king, man, queen, woman is similar. Why? The difference between king and man leaves a vector of royalty or the power. There are a bunch of male and female related words in one grouping, and then there's another grouping in the royal direction. This can be tricked back to the chosen north when the word king shows up in a phrase. In a phrase, it changes the probability of other words showing up in a certain way. It increases the probability of words related to men and the probability of words related to royalty. The word queen appearing in a phrase increases the probability of words related to woman and the probability of words related to royalty. Thus, because the words have this sort of Venn diagram impact on the output probability, they end up subscribing to similar combinations of groupings. Oversimplified, king subscribes to the male and the royal dimensions of the hidden layer, whereas queen subscribes to the female and the royal dimensions of the hidden layer. Taking the vector for king and subtracting out some approximation of the male dimensions and adding in the female ones yields something close to queen. The most important takeaway is that this is more about the properties of language than deep learning. Any linear compression of these core occurrence statistics will behave similarly. So in another word, it's not something magic. It's just the fixed structure that existed in the human language. Summary. You have learned a lot about neural word embeddings and the impact of loss on learning. In this chapter, we have unpacked the fundamental principles of using neural networks to study language. We started with an overview of the primary problems in neural language processing and then explored how neural networks model language at the word level using word embeddings. You also learned how the choice of loss function can change the kinds of properties that are captured by word embeddings. We finished with a discussion of perhaps the most magical of neural phenomena in this space, word analogies. As with the other chapters, I encourage you to build the examples in this chapter from scratch. Although it may seem as though this chapter states on its own, the lessons in loss function creation and turning are invaluable and will be extremely important as you tackle increasingly more complicated strategies in future chapters. Good luck with you. You know what? I won't build the model from scratch by myself. I don't think it's necessary. In the next chapter, we will learn the recurrent neural network. So I will see you in the next video. Bye.